Section 7.1 in Chapter 7 is called instantaneous power. Instantaneous power is very simply the product of the instantaneous voltage times the instantaneous current. We will look at a representation of this, and we'll walk through the relationship to instantaneous power and how we derive it and all. A couple of ground rules. Instantaneous power is always measured in watts. Now, up to this point, you would go like, well, what else would it be measured in? But we're going to see later that there are different types of power. I'm going to drive that home in this chapter. And the other thing is we're going to get introduced to this concept that there is positive power and negative power, and that positive power flows to a device and negative power flows back to the source. Let's look at a representation of this, walk through it carefully, and see what's going on with this idea. Here's figure 7.1 in our text, and it is titled Instantaneous Voltage, Current, and Power in an AC Circuit. Now, one thing I am glad about, doing these classes online is I do have the access to use color and separation between this to explain this very important slide to you. So let me point out a couple of things first. Okay, so here is, let's go through a complete back to zero. Here is a sinusoidal voltage wave. Let me change colors here. And here is a sinusoidal current wave. Okay. All right. Now, also what we're seeing here, and this is strange to us. We've never really seen this before, but what we're seeing here is these areas in here, and what these represent is the power. Okay, and again, we know that power is defined as the power is equal to the current times the voltage. All right, we've always known that. Now, in the DC world, that's really pretty straightforward, but it gets a little more complicated. I don't know what that was. It gets a little more complicated when we start thinking in terms of sinusoidal waveforms. Okay, now we'll walk through all this, of course, but I want to point out a couple of things to you. First off, one thing here is we see that there is a phase angle difference between the voltage and the current. And so at zero, we see that the current and voltage are not in phase. And as a matter of fact, the voltage crosses the 0 point 50 degrees before the current does. Okay, so there's a phase angle there of 50 degrees. The other couple of things I'll point out to you, and he's going to make these points here in the text in just a little bit. He's showing us a peak value of the voltage at 162 volts positive, and that's also represented, in a sinusoidal wave as a minus 162. And we can see that same thing here on the current, that it has a, and I'm sort of guesstimating here on that, but it has a peak value of 7.5 amps and so forth and so on. And so, just walking through a couple of things. What else? It's a pretty busy slide here, isn't it? It's got a lot of information in it. If we have a peak value of, if E sub P is equal to 162 volts, the RMS value, or as we also call the effective value of that, is that value divided by the square root of 2. And if I take that and I plug that into my calculator, I can get the answer that's in your on the slide there, which is 114.5, or as he does in the text, he rounds that to 115 volts, and that's that value there. So the peak voltage at 162 is equivalent, a sinusoidal or peak value of 162 equals an effective or DC equivalent value of 115 volts. We could also just take 0.707, which is, you know where that comes from, right? This thing. But anyway, we won't get into that right now. But we could also just take 0.707 and multiply that times 162, and we're going to get the same answer, right? So we're getting the same thing as we go through this. Then he does the same thing for the peak current. And if I take 7.5 amps and I divide that by the square root of 2, I'm going to get approximately 5.3 amps of effective current at that point. Now, one other quick thing I'll point out to you is here's this phasor representation of this. And again, we want to use the effective values. So he says that the 115 volts is leading the current of 5.3 amps by an angle of 50 degrees. And of course, we're seeing that in our slide or figure here represented with these sinusoidal waveforms. Okay, now hang in here with me. I want to, make this is important that we understand all parts of this. So in this problem, he says, example 7.1 on page 134, let's say I have a sinusoidal voltage that has a peak of 162 volts, right? So we've already seen that there, half of it. And it's at a frequency of 60 hertz. And I also have a current that has a peak value of, he says, 7.5 amps, and it lags this voltage by 50 degrees. And what we're looking at there, of course, is this. Now, since these are sinusoidal values, I need to write the equation differently. And we remember, excuse me, that instantaneous voltage is given by the following formula. You take the peak value times the sine of the angle at the particular point you are in the waveform. All right, so he's just picked one and he says at 120 degrees. So to find that value of 162 times the sine of 120 degrees, I take my calculator, and I'm taking my calculator, and you take your calculator, and you make sure you can do these. 162 times the sine of 162, and what we're going to find out when we come up with that value is that we came up with an answer that is equal to, let's see, what's it come out to? He says 140, yeah, 140.3 volts across there. Okay, so let me fix that on the slide. Time out here. Okay, so I'm showing you this on the slide now, right? You take the sine of 120 degrees, and then you multiply that by 162, and you get 140.3 volts. And I'm showing you that point on that sinusoidal curve, which is right here, right? That's the 140. And then I do the same for the current, but what we have to watch for here is the peak value of the current is 7.5 amps times the sine of 120 minus 50 because of this phase angle right here, right? So the current is lagging by 50 degrees. So we would write that equation as such. So you find the 120 minus 50 is 70. The sine of 70 degrees, which is 0.9396, I think. Multiply that times 7.5, and that gives us this value here, which is approximately 7.05 amps. Okay? Now, so those are the two values that we're able to calculate. Now, what you could do, and what I want to show you here, is that, you could pick all these points on this curve and all these points corresponding on the current curve, and you multiply them together, and that's where this power curve is developed. This is just showing us the product of the instantaneous voltage and current at the different points in the sinusoidal waveforms of voltage and current. And these are showing us the power. These are the power curves. And what I'm also going to see is if I go to this part here, and I take this voltage and I take it through one complete 360 degrees, and I also do that with the current, through one complete 360 degree cycle, then what I'm going to show is that, and it's probably easier to see this with the voltage, but for one complete cycle of voltage here, 360 degrees, I see 2 cycles of power. So the frequency of the power curve is always 2 times whatever the frequency of the voltage and the current is. Now, the everything that we will do, we're not getting into different frequencies between voltages and currents. That's a whole different, another level of study, which we don't do. You do that into, maybe you get into your bachelor's program, you're going out to UNCC. That's a whole different thing there. But this is where we are up to this point. Everything is working at the same frequency. Now, we're not quite done here. Let me show you some of these calculations. And what we haven't done yet is we haven't determined what the instantaneous power is at 120 degrees. So at 120 degrees, what we do is we take power is equal to voltage times current, and that should be actually small p here, because we're talking instantaneous. So if I take 140.3 for my voltage, I multiply that by 7.05 for my current. Okay, if I do that, I'm going to come up with 989 watts. Okay, and that is the power at this particular point, and that would be plotted approximately there on the curve. Okay, now we see the peak value of the curve is 1,000 watts, and at 120 degrees, we're at 989 watts. Okay, just short of the peak. So that's the instantaneous value. Now, what he also does, and let's see if I can find this table 7A, and let's share that, and I'll walk you through that, and we'll be done with this particular section. Very important section. Make sure you understand what I'm doing here, because you guys are going to do this, right? This is sort of a fundamental, thing that you're going to do. Then at some point, we're getting rid of sinusoids and those instantaneous values, and we're going to deal with everything as a effective values, and our life is going to be so much simpler because we're doing that, and the level of the things that we can do is improved with a low level of math and complication because of that. Okay, now we can look at table A together, 7A in your textbook, and it's showing the, it just picked some places and stepped it through. We're at 0, 25, 50, 75, and he goes through that same process that we went through at 120 degrees. Now, if this were my book, I'd have 120 degrees in my table, but he doesn't. But we see where we are with that, and we actually see that peak value that we were talking about of 1,000 watts occurs at the point where the 115 degrees, that's where the peak value occurs for us there. Okay, and then so what he's saying and what he's trying to get us to see here is that we could go through here and we could do all the points on the curve, 0, if we wanted to go in degree steps, we could go 0 through 360, and that is how we would actually plot this power curve, right? We would get all the values, across here, And, I went through one full cycle of voltage, and I see in the 2 cycles of power. And so here's all those plotted values across there. Okay. So that's what he's showing us with this curve. A couple of points, I don't know. I mean, pick a couple of these out, and you can see that 180, that the voltage at 100 and, no, excuse me, yeah, the voltage at 180 is 0. So 0 times anything is going to be 0. So at that point, there's no voltage, and therefore there is no power. All right, and then to sort of wrap this thing up, he goes through with figure 7.2. And since I'm here in the book, I'll go on and go through that with you right now. He says that the voltage, current, and instantaneous power are plotted in figure 1. It attains a positive peak at 1,000 watts and a negative peak at 280 watts. Now, wait a minute. How can you have negative power? All right, so here we go. The negative power means that the power is actually flowing from the load, say the motor, back to the source. This occurs at several places in the curve, okay? It happens here from 0 to 150. It happens again starting at 180. It happens again here. And that's a negative power below the 0 point. And he highlights those for us here, those particular places. They're, each one of them are 50 degrees in duration. And then, although a power flow from a device considered to be a load may seem impossible, it happens in AC circuits. And we're going to understand why that is in just a little bit. And then again, this whole idea of positive, the power curve will always be 2 times the frequency, always 2 times the frequency of the voltage or current. All right. And we see that here over 360 degrees. Okay. All right. So a very important section there. Make sure you understand that you could do those calculations. And then we'll try to understand this idea of negative power and how can that happen. And I'll give you a clue that it's got to have something to do with capacitors and inductors. All righty, let's stop that section and get ready for the next one.